Hi everyone, my name is Shreya Pathania and I'll be presenting on bisection search. Bisection search is a root finding method for continuous functions. Just to recap, a root is when a function passes through the x-axis. Binary search and bisection search are not the same. While the basis of both algorithms are very similar, bisection search works with continuous methods, whereas binary search works with arrays. Bisection search is based on the intermediate value theorem. The intermediate value theorem is when there's 2 points on a continuous line where one point is negative and one point is positive or vice versa. That means in between those 2 points, there is a point that passes through a line. In this case, we have f of a and f of c. F of a is negative and f of c is positive. So that means in between those 2 points, it has to pass through line S. And for bisection search, we want to find an A and B that passes through the x-axis. So the first step in bisection search is to choose an A and B. A and B have to follow the intermediate value theorem or bisection search will fail. And in this case, we have f of A, which is positive, and f of B, which is negative. The second step is to estimate the root by finding the midpoint. So between A and B, depending on what values you get, there will always be a midpoint, and we could find that by using this formula right here. This z value will be a good starting point as an estimation to find where the root is. Now each time we change the root, the interval between A and B will become smaller and smaller until it converges towards one point. This converges through step 3, where we compute f of a and f of z, and we see if it's less than 0. If it's less than 0, then that means that the root is in between a and b. This then changes the value of the midpoint. And then we also check for f of b and f of z if it's greater than 0. This means that the root is in between b and z. Then the midpoint changes accordingly. As the midpoint changes, the intervals become smaller and smaller and converges onto one point. So here's a visual representation of what is going on in step 3. First, we have A and B that we've declared, and the midpoint is closer to B, so therefore B shifts over. Now, our midpoint changes again, so then A shifts over. And with each iteration, the midpoint changes and the intervals become smaller, therefore it converges onto one point. So here is the pseudocode for bisection search. We have A and B that we choose and we find the midpoint. If f of z is equal to 0, then that means our midpoint supposedly is already the root. If not, then we change the midpoint and we converge onto one point, and we iterate through this until it converges. And now I'm going to show you. So now I'll show how this works in code. And here we have a function x cubed minus x squared plus 2. And we're going to find the root. And here we have step 3. And if you run this, we'll find that the root is negative 1. And the 0.0025 we could ignore is just 0.1. And we could verify this by looking at the graph, and here we have the root of negative 1. There's one thing to note in the code that wasn't talked about in the pseudocode. It is epsilon right here. Epsilon is used when A and B are converging. When the intervals become so small, we can't have step 3 going on continuously. So once the difference between A and B is minute, it breaks out of the loop. So the runtime for bisection search is log n. However, the runtime changes based on each case. We have methods like bisection search and Newton's method that are used based on what parameters and variables one knows. The advantage of bisection search is that it will always converge. As long as A and B follow the intermediate value theorem, that means between A and B there will always be a point that is on the x-axis. Also, with each iteration, the algorithm will run faster. Some drawbacks of bisection search is that it has a slow convergence. It also can't detect multiple routes. For example, if you have an interval A and B, it still follows the intermediate value theorem. If there are two routes, the bisection search will only find one route. It also doesn't work for other functions. For example, if you have a function that has a vertical asymptote and it is still continuous, it won't be able to find the root. Also, if you have y equals x squared, because both points on the line will be positive, it won't be able to detect a root. Some applications of bisection search is identifying bugs. It can be used to find change sets that may result in specific behavior changes in code. It could also be used to find the path that may have indirectly fixed a bug. It is also used in structural analysis. Structure engineers have to incorporate natural parameters like earthquake and windstorms, which could all be represented in a numerical model. Now, this could all be solved through Newton's method in bisection search. In conclusion, bisection search is a simple and effective tool. Because it always converges, you're guaranteed to find a root. Even though it has a slow conversion rate, when combined with other methods like Newton's method or secant method, it can be really powerful.